Hi, this is Dr. J here for another installment of I Teach Statistics and Stuff. Today's topic is the almighty analysis of variance, or ANOVA. You may be thinking about ANOVAs like this dude on the right of your screen, but rest assured, we're going to clear it up for you. This video is part 1. It's going to be part 1 in a series of 3. So this video is all about foundations, baby. And then we'll get into the specifics of one-way ANOVAs and factorial ANOVAs in the second and third videos. Let's do it. What is an analysis of variance? Well, it tells us in the name, and they make it sound all complicated and stuff. What color should I choose for this? Let's do, how about yellow? Let's do yellow. All right. An ANOVA is simply a way to compare two or more means. That's it. If you watch the t-test video, what is a t-test? A way to compare two means. So this is where an ANOVA is different. In a t-test, we can only compare two means. That's it. But what if we have 3 or 4 or more means to compare? If you have more means, we're going to do an ANOVA. Now, sometimes we might choose an ANOVA to compare two means if one of those variables has several levels. So that's why I have written here 2 plus. So that's why it's there. But usually it's 3 plus means. But keep it simple, my friends. An ANOVA is a statistical test used to compare 2 or more means. Now, t-tests really used the means. We had 2 means to compare, and a t-test mathematically is just comparing those means to see if they're significantly different. That's really it. However, in an ANOVA, now that we're comparing 2 or more means, we end up using a different way to see if those means are different. And as you can see, we're going to be introducing variance. And that's in the name, analysis of variance, ANOVA. So we're analyzing variance from the mean as a way of comparing 2 or more means. That's it. Now you're going to see this slide. Oh, it's so important I wanted to zoom in on it. You're going to see this slide over and over and over again, like the Duracell bunny. Why? Because the statistic that you choose comes later in the process. Don't just start a study thinking, I want to run an ANOVA. Really, you want to start with your research question, choose the appropriate research design. There's a video on that from my series you can watch. You want to set up the proper methodology. And then last is when you choose the statistic that matches your design and methodology. And oftentimes that will indeed be an ANOVA. Even though a t-test is very good and it's used, it is limited because it can only measure 1. Hold on for 1 second. Hey, I'm recording a video, okay? That's all right. All right, on we go. Let's do it. So, when you get into ANOVA land, that's what we're going to call it. We're going to call it ANOVA land. There's actually quite a bit to talk about because there's many different types of ANOVAs. We're going to see that there's 7, but they have a lot of similarities. And of course, the first place to start is, how are these different types of ANOVAs different? And just like we did in the t-test, we really determine which ANOVA is appropriate by asking ourselves some questions. If you only have 1 independent variable, you're going to do a one-way ANOVA. If you have 2 or more independent variables, you're going to be using a factorial ANOVA. A point to make here is I could have gender as my independent variable, and that's just 1. So if I'm measuring gender as my independent variable, I would do a one-way ANOVA. That 1 independent variable can, of course, have levels. Someone who identifies as male, someone who identifies as female. But it's still 1 independent variable. So it's 1 independent variable that can have multiple levels, but it's still considered 1. One-way ANOVA. What if I wanted to look at 2 independent variables? Maybe I want to look at age and gender. And those could have levels as well. But 2 or more independent variables would be factorial. The second question you ask yourself is a level of measurement of the dependent variable, just like I did with the t-test. If your dependent variable has an interval or ratio level of measurement, we have our good old friends, the parametric versions. If it is a lower level of measurement, it's going to be nominal or ordinal, and that means non-parametric. And lastly, which should also sound familiar from the t-test, look at the type of independent variable. Are you comparing separate groups? I'm comparing males to females. Then I would choose an independent groups, ANOVA. But what if I'm comparing the same group over and over again, repeatedly? Then I would use repeated measures. What if I'm measuring only women over a period of time? Then I would choose repeated measures. Walking through these questions can help you to determine which of the 7 types of ANOVAs. At the bottom, you can see we have 1 type, 2, 3, 4 types of ANOVAs, 5, our 6th, and our 7 types. It can be tricky, and that's why it's important to always ground yourself with the basics. Even when I'm deep into I've had a lot of statistics classes or whatever, sometimes I still need to look at this flow chart because it's easy to forget the basics. So this is a great flow chart. I know because I made it myself. This is how you can ask yourself a series of questions, and they're in order. You want to ask yourself first, how many independent variables are there? 1 independent variable, I'm going to go to the left and do a one-way ANOVA. 2 or more independent variables, I'm going to go into factorial land. Then you ask yourself the level of measurement of the dependent variable. And lastly, type of independent variable, either independent groups or repeated measures. You'll see that there's an additional one under the factorial. Factorial has an option that is mixed. If I have multiple independent variables, sometimes 1 independent variable might be measured through independent groups, while a different independent variable is measured repeated measures. And that would be a mixed factorial design. So we can really cover almost any permutation of comparing 2 or more means. I want to point out there is not a non-parametric alternative for factorial ANOVAs. Last thing I want to point out, the parametric, you can see here I have listed that you would choose parametric or non-parametric based off of the level of measurement of the dependent variable. We might also choose a non-parametric if our total n is under 30, and we might also choose a non-parametric alternative if our dependent variable is not normally distributed. But those will be covered later. Here's a list of our 7 types of ANOVAs. Great. Let's walk through an example because I really think it's useful. So let's say I have a question, and my research question is, do differences, I'm a sports fan, so you may see quite a few sports examples. Do differences exist in batting average? So in players' batting average, I think the S goes there, right? Batting average. Do differences exist in Major League Baseball players' batting average across times of games? I'm going to put days of games too. So once you have a research question, we're going to break it down. What is the independent variable? What is the dependent variable? Well, my independent variable in this example is time and day. So I have 1 independent variable. Now this is going to have multiple levels. I actually might run this with 4 levels. So maybe I have weekday day game, weekday night game. Or I want to look at weekend. Maybe I think that if there is more fans, and then weekend night. If there's more fans, maybe their batting average goes up, or maybe it goes down because they're more nervous. But either way, my independent variable, there's just 1, time of the game, time and day of the game. If I have 1 independent variable, I'm going to choose a one-way ANOVA. I could change this into a factorial ANOVA by adding another independent variable. Maybe my other independent variable is years of playing experience, right? That would be factorial. But as it stands, it would be a one-way ANOVA. So now I'm on the one-way side. So in my question, do differences exist in batting average of players across times of games? My dependent variable is batting average. I know this to be a ratio level of measurement. So that means I already know I'm a one-way ANOVA because I have one independent variable. And if I'm using a ratio level dependent variable, I know I'm going to be parametric. And then let's look at how I'm measuring the independent variable. How I'm measuring this is I have the same number of players. So I would probably do this, maybe I would get 50 players. And I would measure the batting average of these players over those 4 periods of time. So this would be a repeated measures. If I measured the same group over and over and over again. Okay, so don't forget the basics. Now, this first video about ANOVAs is all about the foundations, baby. So, I want to talk about the rules, and by rules I mean basic assumptions. We know that in order for a statistical test to be run, we have to meet some rules or guidelines. And what we're going to find out is these basic assumptions for ANOVAs are very similar to t-tests. But how we run the test is different. I can just sense your excitement. Here are the basic assumptions for an ANOVA, and they're almost pretty much the same as a t-test. When we go through each type of ANOVA, we will go through these more specifically, but suffice to say they're very similar. But wait a minute, what's different? How we run the ANOVA. How we run the test mathematically and statistically is different. Don't be alarmed by the fancy graph on the screen. Stay with me, I promise. I promise, promise, promise. Now, the first question we need to address, it's the elephant in the room, if you're a statistics nerd like I am. If we have more than 2 means, why not just run multiple t-tests? Because we could absolutely do that. We could compare time A to time B using a t-test. We could compare time C to times D using a t-test, and we could compare all those permutations. The problem, however, every time you add another statistical test, the alpha level goes up. And this is going to increase our risk of type 1 error. Type 1 error is when you reject the null when you shouldn't have. And when we run more and more and more tests, the alpha level goes up and we increase our risk, which lowers our accuracy. So the general rule is when you can, you want to run as minimal amount of statistical tests as possible. So that's why we prefer to do ANOVAs when we have 3 or more means. Let's get into the language of the ANOVA. If I could do like a sexy French or Spanish accent or British, any kind of accent, I would do it. But alas, I cannot. So we've already talked about the fact that the ANOVA, per the name, ANOVA, analysis of variance, we're going to be talking about variance. What is variance? Variance refers to how each individual score varies from the mean. Sometimes a score will have a high variance from the mean. Sometimes it'll be closer to the mean or actually be the mean. And I've used this simple diagram. In our example, independent variable was the time of the game. So depending on the time of the game, I wanted to look at that baseball player's batting average. So this line here is visualizing the mean. Okay, so this is saying as the time of game changes in a certain way along the x-axis, the batting average goes up. Okay, variance would be how much each individual score, these dots, here we have baseball player A, B, C, D. If I really ran this, I would have 50 dots because I had 50 players. We're looking at how each individual score varies from the mean. This first dot varies this much from the mean. This dot up here varies more from the mean. This dot is very close to the mean. So in essence, what we're looking at, we're seeing how each individual score varies from the mean. That's what variance is. And we're going to be able to quantify it and do some fancy math and get a significance number, and either we accept or reject the null, and it's all great. Okay, I want to point out something else, and that is sum of squares. You don't have to be a mathematician to understand these concepts. I'm not a mathematician. Maybe you like that. Fantastic. I'm not a mathematician. However, when we talk about ANOVA, we're assessing variance. So we have to talk about it, at least a little bit. So this video is meant to give you some basic foundation. So when you see these words later, when you see these terms in the SPSS readout, you know what the hell we're talking about, at least a little bit. You can also impress your friends with this extra knowledge. Yes, the sum of squares principle, believe me. Nothing is sexier than knowledge. Ha ha ha. Okay, what we're going to find out is behind the scenes, if you did an ANOVA by hand, because that's possible, just a lot of math, you can use an Excel spreadsheet to help you. If you do an ANOVA by hand, or if we type numbers into a program like SPSS, it's going to be using sum of squares. Let me change colors here, just so we can see I'm talking about something different. Let's do orange. All right. If we took each individual score and its difference from the mean, okay? Let's say that this player was 10 points above the mean. This player was actually 15 points below the mean. So what the math is going to do for us is it's going to calculate the variance of each score from the mean. And then it's going to add them up. So we're basically finding a way to mathematically find in totality how much all of the scores varied from the mean. If all the scores varied from the mean a lot, we might be more likely to find a significant difference between groups. If the scores didn't vary much from the mean, we may be less likely to find a significant difference between the groups. But here's the thing. When we take the sum of each score's difference from the mean, if we did that just as it is, we would get 0. If we took each of these points, found their difference from the mean, and then added all those up, all the differences from the mean would add up to 0. Because that's what exactly the mean is, halfway between the top and the bottom. So that's why we have to sum the square. And I purposely wrote this bullet point with the parentheses where they are to make this point. The sum of squares is the sum of parentheses, each score's distance from the mean squared. So we first, behind the scenes, each score's distance from the mean is squared. And then we add up each individual score's distance from the mean squared. That's different from if we took each score's distance from the mean, added them up, and then squared it. No. We take each score's distance from the mean, square it. And then we take the sum of all of those. Look at how smart you're going to be. Oh, wait, we got more. The how of ANOVA. I put these terms on here precisely because you're going to see them in the readouts. We just talked about sum of squares. We talked about why we had to square them. Look, it's in the readout from SPSS. I'll be. So some more terms you're going to see. You're going to see degrees of freedom. Depending on which type of ANOVA you're talking about, degrees of freedom is n-1. So if I had 50 baseball players I were using as subjects, one of my degrees of freedom would be n-1, or 50 minus 1, which would be 49. Other times we use different definitions. Maybe it's my number of groups. I had 4 groups because I'm comparing weekday day games, weekday night games, weekend day games to weekend night games. 4 groups minus 1. So sometimes my degrees of freedom for that is going to be 3. So we'll see those. It doesn't so much matter how we calculate them now. And then we're also going to see mean squares. Mean squares is calculated from sum of squares. Look at the top. Mean squares is going to be the sum of squares divided by the degrees of freedom. So if you took this number, 6,367.321, that's our sum of squares. And if we divided it by degrees of freedom, here it's 2, we would get the mean square. So here it says what SPSS calls sum of squares. It's actually another variation from it. But you're going to see mean squares. And the reason why we have to convert means, we have to find the mean squares, is because that's what we're going to use to find our F ratio or our F statistic. When we did t-test, when you looked at the SPSS readout, you were looking for the t-score. Now we're looking for an F score. I know it's confusing because it's ANOVA, it doesn't begin with an F, but over time you'll get it. So a certain mean squared value divided by another mean square value. In this case, we divided this first mean square divided by the second one. It gives us the F ratio, which is our F statistic. So these are just the terms to get used to. That F statistic is the same thing as F obtained. I think a little orange is easier to see. When we did a t-test, we had a 2-tailed hypothesis testing distribution, and we found our t crits. Here was our t crit on the negative side. Here was our t crit on the positive side. And then we found our t obtained. If the t obtained was out here, it's in the critical region, we reject the null. Same idea, but for an ANOVA, for reasons we aren't going to get into, an ANOVA is 1-tailed. It's the same idea. Using the information that you have behind the scenes, you would calculate F critical values, and we would plot that. And then when you get your F obtained, the F obtained in this example was 29.306. 29.306. So here they actually put 29.3. They rounded it to 29.3, our F obtained. And it just turns out, based on where our F critical is, our F obtained is in the critical region, which means you reject the null. The means are significantly different. As a guideline, I don't want to say always, but typically our T critical values are somewhere around 2. And our F critical values from a table using degrees of freedom and a bunch of other things is usually around 3. Usually. So we can see here the F critical for this example, 3.74. All right, last topic. We're almost done with the foundations, baby. I talked about variance, but there's more to talk about. Let's talk more about variance. This is our last topic for the first video. You got it. We know that an ANOVA is an analysis of variance. We know that variance is looking at how each score varies from the mean. We know that when we do the math behind the scenes, we have to sum all the squares of those variances from the mean, because if we don't, the sum of all the variances from the mean would be 0, and that wouldn't be mathematically useful. But what about the types of variance? Typically, the F ratio, which we saw before, remember the F ratio was our mean square of one group over mean square of another. Another way of looking at that, the mean squares is our mathematical way of looking at it. But our more logical way of looking at it, or theoretical way, is our F ratio is equal to explained variance, however much explained variance there is, divided by the amount of unexplained variance. This is really the F ratio in theoretical terms. Ideally, you want the explained variance to be greater than the unexplained variance. We like explained variance to be higher because that's the variance that we know we can explain. In the example that I gave with the baseball players, explained variance would be differences in batting average due to the time of day. That's explained. So we want that to be higher. And we also like, in any type of scientific study, to keep unexplained variance low. What are some things that could account for unexplained variance? The mood of that player, something else going on at their life that you're not aware of, what they had for breakfast. Maybe they had a new batting glove that affected them. There's things that we cannot control, particularly psychological factors like their mood. You can't control that. So we want to keep that low, but we know it's there, so we have to address it. And if you notice, mathematically, if our explained variance as a numerator is higher and our unexplained variance on the denominator is lower, then we're going to have a higher number. And the higher the F number, or F obtained, the higher that is, the more likely it is to be greater than our F crit, which is usually around 3. And we're more likely to reject the null or find a significant difference if there is one. Not that finding a significant difference is always what you want, because a null finding is just as valuable as rejecting the null. Now, how we define explained versus unexplained is going to change based on the type of ANOVA, because we have so many different permutations of ANOVA. How we define what is considered explained variance versus what is considered unexplained variance is going to change. So I'm going to give you an example, even though we're going to talk about this more in the future videos with the specific types of ANOVAs. The example that I gave you earlier was a one-way repeated measures ANOVA. Our independent variable was time of day, and our dependent variable was batting average. We measured the same 50 players 4 times because we had 4 different levels of time of day. So here we go. In a one-way repeated measures ANOVA, we're going to have 3 types of variance. What we're going to find out is in a one-way independent groups ANOVA, we're only going to have 2. So you see it depends. But no matter what type of ANOVA you do, there's going to be some type that is considered explained variance, and there's going to be some type that is considered unexplained variance. And when we do our F calculation, we take the explained variance and divide it by the unexplained variance. That is what is the same for every type of ANOVA. In this specific example, let's break it down more. In a repeated measures ANOVA, no matter if it's one way or factorial, anytime you have a repeated measures ANOVA, we're going to have what's called a between subject variance. If I measure subject A 4 times, 1, 2, 3, 4, that same subject is being measured 4 times. There's always going to be some variation within that subject between the treatment times. So even if I control everything I can, maybe based on their mood, one day to the next, there's going to be some variation. Well, actually, that's not the example I want to give, and I'm okay with going back because nobody is perfect. Let's put it this way. No matter what, even if you measure the same person, even if you measure the same person, there's going to be some variation. And we know that's going to be there. And because it's going to be there for everyone, this is considered a constant. But I still have it in here. It's shown as yellow. We kind of put that aside in a repeated measures ANOVA. We know it's there, but we put it aside because it's the constant for everyone. So if it's the constant for everyone, it's not really going to change what we're looking at because that's assumed to be a constant or relatively constant. In a repeated measures one-way ANOVA, here's what we care about. Our explained variance is called treatment within, and that's what's shown in this pie chart as red. This would be explained variance, variation in players that is explained by your independent variable. And our independent variable is time of day. So our treatment within variance is the variance in that player's batting average over the 4 times because of the difference in time. Batting average is lower during the day, it's higher at night. That is an explained variance. It is a variance between the 4 scores for the same person that is due to the independent variable. Then we have unexplained variance, and this is the error within a subject. Within that subject, mood, nutrition, other things, these are things that will undoubtedly creep in. No matter who you are, we're humans, we're not robots. No matter who you are, there's going to be some variance just because of that person. And this would be variance not due to batting average changes is because of time of day. And that is called the error within. When we do the F ratio for a one-way repeated measures ANOVA, the F ratio is mean squares treatment, which is explained variance, divided by mean squares error, which is unexplained variance. So remember, it's always going to be explained variance over unexplained variance. It's just that what we consider to be the explained or the unexplained variance changes based on the type of ANOVA. And this is the formula we would see with a one-way repeated measures ANOVA. Now you're ready, folks. We know the basics of an ANOVA. Compares 2 plus means. We're using variance from the mean, and we're going to mathematically calculate that into an F statistic that we compare to the F crit to see if it is statistically significant in the critical zone. We know that the F ratio is really a ratio of explained variance over unexplained variance. The explained variance is a variance in the dependent variable due to the independent variable. That's what we're looking for to see if it's different. And the unexplained variance is variance within individuals or groups that you cannot change. We want to keep the unexplained variance low, the unexplained variance high. When we do that, we're more likely to have a high F value, and we're more likely to see differences between groups. You ready to go, folks? Peace out. I'll see you for part 2.